All right. Now, Lagrange multipliers are for a constrained max-min question. So if you have an equation, x squared plus y squared is equal to 1, and you're trying to maximize or minimize this function, that's when you use the Lagrange multipliers. However, if you have an inequality, that actually becomes harder because here's what's happening. You have, if this is just equal to 1, it will be a circle. It'll be a circle of radius 1. What if it's less or equal to 1? What does that contain? Everything inside the circle. Okay. If it's less or equal to 1. So if it's exactly equal to 1, it'll be just the boundary. If it's less or equal to 1, it'll contain everything inside the circle. Okay. Now, you have two kinds of max-min problem here. When you're given, without this condition, when you're just given this function and you're asked, what's the max and min of this function, what would you use? You would use the critical point, right? So you take the gradient of this equal to 0, and setting that equal to 0, you figure out where that is attained, and then you use the second derivative theorem to figure out if it's a saddle point, a relative max, relative min, and then judging from there, you can kind of guess whether it's a global maximum or min, right? So that's what's being applied if it's inside the circle. Okay, inside the circle, you'll be looking for critical points, but right on the circle, what you're getting is you get boundary condition as a constraint, x squared plus y squared equal to 1, and there you would use the Lagrange multiplier. So if you have a max-min problem of a function inside some domain, given domain, you actually are faced with solving this question using two methods. So such a question is number 1, inside number 1, inside the domain, look for critical points. And then on the boundary, use Lagrange multiplier. Okay? That's what you have to do. It's similar to calculus 1 case where if you had a function over a closed interval, inside the interval, what do? You have to figure out all the critical numbers inside the interval, right? But then you also had to evaluate the function at the boundary. Now the problem with having two variables is that the boundary is just not two distinct points. It's actually a whole infinitely many points, right? So you don't know which one to evaluate. So you have to figure out where the maximum and minimum of the boundary is. And then using that, you have to compare it with the max min inside the boundary. All right, so let's continue with this question. Let's see what we can do. So first, we will try to find the gradient. And let's see. What do you get if you differentiate this by x? You have to use a chain rule, right? So you consider this as this as 3 times e to some function, and that doesn't change. But then this inside function has to be pulled out, and that one has to be differentiated by x. Let's not write it yet. So let's just say derivative of x of 3 negative xy is equal to this, okay? Now, if you differentiate this by x, what do you get? What do you get if you differentiate this by x?
Negative y over.
Negative y over. So at the end, you get negative 3 over 4 e to negative xy times y. Maybe I should put y here. And then, what would you get if you differentiate by y? The same kind of procedure, right? This will come down and you have to differentiate by y. In that case, you'll have negative x over 4 instead of negative y over 4. So using those two, you get the gradient of f equal to negative 3 over 4 y times e to the negative xy over 4, whereas over here it's negative 3x over 4 e to negative xy. That's the gradient. Now, when can this equal to 0? Because we're looking for the critical points first. Can exponential functions become 0? No. So for this entire thing to be 0, you have no choice but to have y as 0, right? For this entire thing to be 0, you need y as 0. How about here? X has to be 0. So this will only happen when x and y are 0. So is the only Now, if this was an unbounded constraint question, then you would further proceed and actually use the second derivative test to see if it's a saddle or relative max and relative min, and then to further analysis. But here we don't have to go as far as that. We just need the critical point and the value at that point. So what's f of 0, 0 then? This will be 0, so you get 3 times e to the 0th power just 3. Okay? So we just know that at the critical point, the value of the function is 3. That's all you need, because I mean, we know that if the max or min happens at the boundary, it must satisfy the Lagrange multiplier equation. If it's max or min inside the boundary, then it must occur at critical points. And those will be just finitely many points. And if we have finitely many values for these functions at these finite points, then we can just look at those and say, hey, this is the maximum one, that's the minimum one, and that's it. Okay? So that's why we don't have to differentiate this twice to get the Hessian and all that. We don't have to do that. Okay? So thankfully, we're going to stop here. Now let's look at on the boundary. For the boundary, we need to do this, right? So what do? We have gradient of x squared plus y squared is equal to 2x, 2y. Okay. And that's, what's that? That's it. Okay. And then, doesn't look so nice. Let's see. So I should really have said something here. So for here, this is on the boundary. And by the boundary, I mean that's when this is exactly equal to 1. When the inequality is replaced by equality, that's at the boundary of the domain, right? So that's what we have. And then on here, we have to use the Lagrange multiplier, which says I have to set this equal to some multiple of this, or vice versa. Which one should I multiply by lambda? I think it's easier to multiply lambda here. Yeah. All right. So let's just say gradient of f is lambda times gradient of g, where g is this one. That's our Lagrange multiplier. In this case, we have negative 3 over 4y e to the negative xy over 4, negative 3 over 4x e to the negative xy over 4, equal to, when you multiply lambda, you get 2 lambda x, 2 lambda y. So I multiply lambda to this one and set them equal to each other. Okay, and then we have the following. We have that negative 3 over 4 y times e to the negative xy over 4 is equal to 2 lambda x and negative 3 over 4 x e to the negative xy over 4 equal to 2 lambda y. Okay. Now, it looks like a system of equation that it's impossible to solve, but let's do this. If you have an equation and if you divide both sides by the same thing, shouldn't they still be equal? Right? Yeah. That's right, right? If you and the other guy have the same income and both of you, your salaries got slashed by half, that means you still have the same income, right? So if you divide both sides by the same thing, it's the same thing. But see, this is what I'm going to do. I'm going to say negative 3 over 4y e to the negative xy. On this side, I'm going to divide by negative 3 over 4 x e to the negative xy, right? And on the right side, 2 lambda x, I'm going to divide by 2 lambda y. Okay. Am I dividing two sides by different things or the same things? It says that they're the same thing, right? So although it looks like I'm treating both sides unfairly, I am doing the same procedure to the left and right. Do you agree? Right. So would the equality hold or not? Yeah. The equality still should hold. Are you following my argument?
Yeah.
Okay. As long as you're doing the same thing to both sides, the equality should still hold. And on the left side, I divide by this, and on the right side, I'm dividing by this, which is actually the same thing as this one. So the equality should still hold. Now, do you see that a lot of cancellation occurred? Oh, sorry, this should be 4. That's why you were looking at it, probably. Oh, by the way, the one thing that you have to be careful when you're dividing both sides is you have to make sure that you're not dividing by something that's 0. But we know that lambda is not 0, because if lambda is 0, then you're looking for the critical number, right? But we know that the critical number is only at 0.0, which is inside the circle. So it never happens. So that's why I was confident when dividing. Now look what I have. What do you get after all this calculation? So we get that y over x is x over y. Right? And we can cross multiply. If I cross multiply, I have y squared is equal to x squared. Okay. And then remember, we've only used this equation, but what do we have to include? The constraint must be considered as the third equation, right? So this has to be included. So we take x squared plus y squared equal to 1, and then replace y squared by x squared because we have the result that x squared and y squared should be the same. So I replace it, and I get x squared plus x squared is equal to 1, which means x squared twice of x squared is 1, and then divide by 2 both sides. And we get x equal to plus or minus 1 over square root of 2. Okay? And because y squared is the same as x squared, y would also end up being plus or minus 1 over radical 2, but they don't necessarily have to be the same sign. So we actually have how many points? Oh, by the way, these are called Lagrange points. How many Lagrange points do we have? 4. Okay. Plus, 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 minus, minus, plus, minus, minus. And for all of them, we have to compute this. And let's see. So let's figure it out. So on 1 over radical 2, 1 over radical 2, what's f? 1 over radical 2 times 1 over radical 2 is 1 over 2 over 4 is 1/8. So this is 3 equals 1/8. Okay. And then
Wait, how'd you get 1 over 2?
yeah, square root of 2 squared is 2. So
Alright.
this will become 1 over 2, and we divide by 4, it's 1/8. And that's actually true for both of them are negative. Okay? Because negative times negative is positive, so you get the same answer. But what if you had f of positive square root 1 over radical 2, but the other one is negative? Yeah, in that case, it would be 3 times e to the positive 1/8. And f of negative 1 over radical 2, 1 over radical 2, this will value to positive 1/8 also. So these two will have the same value, these two will have the same value. Now, we have 5 points to compare with. We have to list the highest to the lowest. What's the maximum? So the question is this 3 bigger than this or less than this? What do you think?
Is that 3 bigger than those 2?
So 3 and 3 times e to the 1/8, which is bigger?
3.
3 is 3 times e to the 0th power. 1/8 and 0, which is bigger? 1/8 is bigger. Okay. So actually this is the largest. Okay. This is largest. That's the middle one. And this was the smallest. Okay? So the answer is you have max of 3 to the e to the 1/8 at or okay, and what's the min? Or okay, so that's the answer. Okay, so final remarks. I purposely chose to take the entire thing as f of x, y, but sometimes you can be smart about finding your max or min and just take a portion of the function to represent the whole. Okay? So let me explain what I mean by that. So look at this function again. If negative xy is maximal, wouldn't the entire function be maximal? Do you agree? If negative xy is the smallest, wouldn't the entire thing be the smallest? I mean, exponential functions, if you have some big one and small one, which one is bigger? Just like that. So what really matters is what's inside the exponential function. So Maybe we can just take that. So we can solve this question with our target function to be maximized or minimized as just thing inside rather than the entire thing. That would have saved us a lot of work. So let me briefly explain how that would be done. So if you're to solve it that method, so method 2, you would just consider h of xy as negative xy over 4. Simple. And then you would say, note that f is max min when h is max min. Well, this is not the only way. You could have chosen hxy as just negative xy, deleting the 4, because it's the same thing happens, right? Or you can even say hxy is just positive x comma y. In that case, when f is maximum, h is the minimum. Or you would do that. Right? So you can save a lot of time by doing this trick. Okay? And then if you do gradient of h, what's that? It's negative y over 4, and then positive negative x over 4. And just say this is lambda times, well, the critical number already, you can see that it's when it's 0, 0. So differentiating and finding a critical point, that's easy. And then when you take 2 lambda, 2x, 2y here, then that's again very, very simple. So calculation going through this route will be very simple. It's you can try to complete the rest. And after some point, it's almost the same thing, but we don't have to do that strange algebraic trick if you could notice that this is what we need to do. Right?
So that's all we have to do.
You could have done it a lot simpler if you did it this way. But I just wanted to demonstrate how it could be done in that complex case. Okay? But this is a lesson for us that choosing your target function wisely can save you a lot of time.